video, we would like to show how our application can be used to calculate farm level water energy food environment nexus index. On this homepage, we provide general information about the concept of WEFE Nexus and basically how performance of crop producers can be estimated within WEFE Nexus, because the application I will be showing today is basically for crop production, olive production more specifically. Also, here user can see what this application enables him to do. Once we click on Calculate WEFE Nexus Index, we can basically see their page with the model itself. Each step here has a help file or a help tab, which is really advisable to check before basically performing this step. So we need to upload farm level data. It should be in CSV format, and this application works with cross-sectional or pooled data. All the preliminary data processing should be done before this data is uploaded. So we upload our farm level data, and our first step will be to estimate technical efficiency. Application allows to estimate technical efficiency because based on developed composite indicator, we account for the economic performance of farms via their technical efficiency, which reflects link between water and energy as inputs of the production function and food as output of the production function. So here we select our output, and here we select all our inputs: water, fuels, land, labor, machinery, fertilizers, pesticides, herbicides, and insecticides. So these are inputs which are relevant for our production function. This is just as an example. Also, if a parametric approach is used for the estimation of a technical efficiency, user can upload data on contextual variables, continuous or categorical, and in the case of crop production, specifically these variables can be climatic variables, continuous ones, so sum of precipitation, mean temperature, because crop production is really sensitive to climatic conditions, or categorical variables such as region or agroclimatic zone. So in this case, we control for these factors. Application allows you to estimate technical efficiency using either non-parametric or parametric approach. So non-parametric 1DA is like technical efficiency here is estimated using package benchmarking, and for the parametric model stochastic frontier analysis we use package frontier. And here we briefly talk about the advantages and limitations of each approach. So we will estimate technical efficiency using non-parametric approach, and here we need to specify orientation of our model and returns to scale. So again, in help tab we provide super briefly like the difference between input and output oriented models. So in our case, we want to minimize the use of inputs to produce a given level of output, and also an assumption behind returns to scale is important, whether you assume that the production process is characterized by constant returns to scale or variable returns to scale. If you select a parametric approach stochastic frontier model, you should specify which production function, like functional form of the production function, should be estimated in your model. Cobb, Douglas, or Translog, they are the most commonly used. Here we provide basically the formulas and also the type of the model: error components frontier or efficiency effects frontier, and here we provide references. But as said previously, we would like to estimate technical efficiency using the DEA model, and when we run the model we get descriptive statistics for technical efficiency values, also number of farms and share of farms that have like technical efficiency values within specific range, distribution of technical efficiency values, and how the frontier looks like. In the updated data set, we can see that at the end we have our efficiency, technical efficiency values added as a variable. And now we would like basically to calculate our composite indicator values. So technical efficiency in our composite indicator is just one subcomponent to account for the link between water, energy, and food, but we also have other performance indicators that we would like to incorporate in our composite indicator. We have both good and bad performance indicators. Here we explain the difference. So good are the ones with larger values indicating better performance, and bad are vice versa. Why it's important to distinguish them? Because in our approach we suggest to estimate endogenous weights for our components of the index, and if we have both good and bad performance indicator, we need to use directional distance function, so this benefit of the doubt model with bad indicators. So among good performance indicators we have our efficiency values, and we also have some sustainable practices used, such as pruning of branches, because we are talking about olive production, and also usage of renewable energy, while bad performance indicators are soil stress indicator, nitrogen emissions, and pesticides, herbicides, insecticides pollution. Here we won't specify particular constraint for weights, but you can do it. And when we run our WEFE Nexus Index, we can see descriptive statistics for our subcomponents of the index, and here summary statistics and basically distribution of the composite indicator values. And at the end here you can download dataset with a special variable which contains the values of the composite indicator. We hope that this video was helpful for you, and you will find our application useful for your data analysis and assessment of performance for your decision-making units.